So we're working on a proof of the general inclusion-exclusion formula for the union of n sets. In general, I try to avoid subscripts in the text as much as possible, but sometimes you have to bite the bullet and use them because we're talking here about a union of A1 through AN, and it's inevitable that I will need subscripts. So let's remember what the formula is. I'm interested in expressing the size of the union of n sets, A1 through AN, in terms of their intersections. And the use of this is, we've seen previous examples. Very often when you have a bunch of sets, it's easy enough to calculate the size of the intersections of some collection of them. And it's not so obvious how to count the union. In fact, it's clear that how complicated the union can be if you look at the complication of this formula. But what it says is that I can find the union if I can find the sizes of all the different intersections. So S here is ranging over the set of possible subscripts that the A's might have, and I choose some set of subscripts, and I take the intersection of those AIs that are in the set S with an appropriate sign, which is going to be even if S is odd, because that'll make the exponent even, and -1 to an even number is 1. And if S is even, then this exponent will be odd, so the even size intersections are going to get a negative sign. And the only small constraint is that we're looking at non-empty sets S. So this is what we're trying to prove. It's a review of what we've seen before. Okay. Now I'm going to introduce two abbreviations. One is just for convenience, that if I have a set S that's a subset of 1 through n, if S is not 0, I'm just going to let I sub S stand for the intersection of those A's that are specified by S, the AIs that where I is in S. But I'm going to introduce one further abbreviation for convenience, and it's also actually a logical abbreviation. I'm going to say that I sub the empty set, the intersection of the empty set of indices, is going to be the union of all of the A's. And we can rationalize that definition by thinking about quantification over saying that elements in I sub empty are the elements that are in A sub I for every I in empty, and that means it's vacuously true, so every A works. Whether you follow that logic about how membership in the empty set, quantifying over membership in the empty set works, let's just accept this as a convenient abbreviation. So I sub phi is the union of all of those A's. That's what I'm interested in. So rephrasing, you're just plugging into the stated formula those abbreviations. First of all, I replace the union by I sub phi. And second, I replace the intersections by I sub S. So there's the rephrased formula in using the abbreviations. But now I'm going to do a small simplification by pulling over the I sub phi to the right hand. I'm going to pull it to the right hand side. I'm going to subtract both sides, the size of I sub phi. And that way, when I do that, I'm going to be able to just consider all subsets instead of non-empty subsets. So now I've simplified the formula by subtracting the size of the I sub empty set, the size of the union from both sides, and I get that 0 is equal to this sum over all possible subsets of indices of the intersection of the AIs that are specified by S to the appropriate sign of 1 or -1. And let's just move that and line it up. So there's the formula that I'm now trying to prove. Okay. There's a further simplification that we might as well make now just for convenience. Notice that the exponent here doesn't really matter too much, because what matters is that the signs are alternating. Since it's equal to 0, if I multiply both sides by -1, it's still 0, and multiplying both sides by -1 has the effect of replacing the size of S plus 1 by the size of S, period. So that's a slightly simpler formula. This is what we're aiming to prove. And I'm going to call the left-hand side of this sigma sub n, just briefly, so that we can have a name for it that's not writing the whole thing out. Okay, so the strategy of the proof is going to be, as before, we're going to try to get this idea of how many times is a given element A counted in sigma sub n. And we're going to try to claim that the number of times that A is counted in sigma sub n is 0. This is what we did before when we were proving the inclusion-exclusion principle for two sets. We said how many times is an element that's in A counted, and how many times is an element that's in B counted, and how many times is an element that's in A intersection B counted. And we derived inclusion-exclusion for two sets that way. We did the same thing with three sets, where we classified elements by how many times they were, the intersection of two of them was counted and how many times the intersection of all three is counted. Now we're going to formalize this. And looking ahead, number of A is going to mean intuitively, it's the generalization of the argument we saw before, the number of times that A gets counted in this sum. And the claim is going to be that A is counted 0 times. So what it means is that the sum is going to really turn out to be the sum over all possible A's of the number of times that A is counted, which is just going to be a sum of zeros. It'll be 0, and that's how the proof is going to be organized. So the key step in making this formal and precise is, how do I give a rigorous definition of the number of times that an element A gets counted in this sum? Well, the trick is going to be to introduce the member function for the intersection. So m sub s of A tells me whether or not the element A is in the intersection of the capital AI's specified by S. So it's 1 if little a is in the intersection specified by S, and it's 0 otherwise. Okay. Now, looking at sigma n, I'm going to say that I can now replace I sub s by the sum over all possible elements of m sub s of A. Let's think about this for a minute. An A that's in the intersection contributes 1, and an A that's not in the intersection contributes 0 to this term. So the sum of over all possible A's of these 0, 1 valued terms is exactly the number of elements in the intersection. So I now have a nice formula for that I can replace the size of I sub s by as simply a sum over all possible A's of m sub s of A, which I've just done. Now, again, this is the target. We want this to be 0. Well, let's fiddle with the sum a little bit to make it a little bit more workable. I'm going to distribute the minus 1 to the s's to push them inside the summation. That's just the distributive law of multiplying a sum by a constant. You multiply each of the things being added by that constant. And next, I'm going to do a standard trick, which is I'm going to switch the order of the sums. Remember, a sum like this, we're putting order on it. It doesn't really matter. It's just a bunch of collections of terms that are determined by S and A. And I'm looking at this term m sub s of A. The order in which they appear is arbitrary. I've decided I'm going to, for each S, I'm going to sum over all the A's, but I could equally well just sum over all the A's for each S. And that turns out to be a useful trick, because now I'm summing over A's of this formula, and this formula, in fact, if you think about it, is the one that's telling me how many times A is counted in the sum. So this is the term that is the formal definition of the number of times that A is counted. And what our objective, again, is to show that this formula, summing over all possible sets of indices of the m sub s of A, the membership function for A being intersection with the appropriate sign, that this sum comes out to be 0. Okay, so again, the sigma sub n that we're interested in is just the sum of all of those sharp A's as we formulate it. So all I got to do is show that this guy is 0 and the proof is finished. Well, now I'm going to make the step which I've been postponing. Usually the inclusion-exclusion formula is stated in terms of not just the sum over all possible S's, but over the S's of size 0, and then the S's of size 1, and the S's of size 2, and so on. There's no particular reason to do that, because I'm just summing over all the S's in any order that I choose. But at this moment, it's going to turn out to be advantageous to break up the sum into by the sizes of S. So I'm going to rewrite the sum over all S's as the sum over the size of a possible S from 0 to n of the sum over all of the S's that are of size J. So these two sums are the same. I've just I've just grouped them differently. So now I'm grouping the terms here. Instead of just by s, I'm grouping them with all of the small s's first, and then the of size 0, and then the s's of size 1, and so on. So this is the formula that's, again, counting the number of times that a is counted, and I'd like that to be 0. Well, let's look at this subterm to see if we can make sense out of it. In fact, we'll be able to calculate what this is. The trick is that this is going to turn out to be a binomial coefficient. Let's understand the reasoning. So we're looking at the sum over all of the intersections of size j of whether or not the element a is in the intersection. That's what this means. Okay. So looking at this term that I want to understand, let's just look at a concrete example. Suppose that the element a that I'm looking at happens to be in exactly 5 of the capital A's. It's in A2, A3, A4, A8, and A9, and that's all. So A happens to be in exactly 5 of the sets that I'm interested in the union of and that I'm taking intersections of. All right. Well, that means that m sub s of a is 1 when a is in the intersection of all of the ai's where the indices are in S. Well, if S included any index other than these a's, then ms of a is going to be 0 because a is not in any of the other a's. So in order for this to be 1, S has to be a subset of the sets that a is in. S has to be a subset of 2, 3, 4, 8, and 9. All right. Well, knowing that, let's look at a concrete case where instead of looking at the sum over j, let's look at the sum over those s's of size 3. So we know that a is in exactly the set specified by this s, and I'm interested in looking at s's that are subsets of these 5 elements that are of size 3 and taking the sum over all of the elements a that are in the intersection of 3 of the 5 things. And basically what I want to know is how many s's of size 3 are there, because every one of these s's of size 3 is going to contribute a 1 for the a. So the number of s's of size 3 is going to be the size of m sub s of a for that a. Okay. Well, there are 5 choose 3 such subsets. And that means that I got my formula, that the sum of m sub s of a, for any fixed a, the sum over all the s's of size 3 is the number of those s's that which would allow this to be 1, namely all of the ways of choosing 3 out of these 5 indices. It's 5 choose 3. All right, now we can state the generalization. If a is an element that's not just a member of some 5 particular of these sets A1 through N, suppose it's a member of exactly K of them, then what I know is that m sub s of A is 1 exactly when I'm only intersecting the K elements that this little a is a member of. And if I'm summing over those sets S where this is 1, which are of size J, there are exactly K choose J of these intersections when m sub s of A is 1. So that means that we figured out, generalizing the 5 choose 3 example, that that this term, the sum over all of the s's of size J of m sub s of A, is K choose J. And now we're practically finished, because remember we were working on this formula that told me the number of times that A was counted in the sum, and it involved this summing over all the sets of size J of m sub s of A. And now I know that this piece of the formula is simply K choose J for the A that by hypothesis is in K of the sets that we're intersecting. So this sum becomes, instead of a sum from 0 to n, it becomes a sum from 0 to K of K choose J. But this ought to look like a familiar formula, because the sum of K choose J with -1 to the J as the exponent is exactly the binomial expansion of 1 minus 1 to the K. And that, of course, is the same as 0 to the k. It's equal to 0, and we're done. We've gotten through this challenging slide full of equations, and I hope that the net effect is that it will enable you to reread this proof and follow it step by step, and even some of the motivation of what's going on in the background.